Hey folks, here we are, section 4.4. It's called graphing functions. There's not a whole lot to this section. This section is basically just a capstone of what we've done so far in chapter 4. So in other words, there's nothing new in this section. We also might, harken back to some stuff that we've learned in, previous chapters, such as, vertical asymptotes and horizontal asymptotes. But really, there is nothing new in this section. On the first page of this section, your text does have a box called Graphing Guidelines box, and it summarizes everything that's going to take place in this section, or everything that can take place, because we're just graphing functions. So you will see nothing new in that box. So we're just going to practice by doing some examples. I have about 3 of them to do here. So the examples are very straightforward. Directions are very straightforward. Make a complete graph of the following functions. The first one is f of x equals x cubed minus 147x plus 286. The second one is the rational function f of x equals x squared over x squared minus 4. And of course, we're going to have a trig one to look at, which is f of x equals x plus cosine x on the closed interval 0 to pi. So I'm going to head off to the chalkboard and we're going to do these. All right, folks, here's section 4.4 in theory. You can do everything in this section. You have all the tools at your disposal. I still thought we would do a couple of examples just to make sure you're dialed in. So the first function that we're going to make a complete graph of is f of x equals x cubed minus 147x plus 286. So here's how I start. I may make some observations that it's a polynomial function, so I know it's continuous everywhere. It's a cubic polynomial. The leading coefficient is positive, so it's an odd degree polynomial. Leading coefficient's positive. So I know that end shooting up, this end shooting down. But let's get on with doing some calculus. The derivative, 3x squared minus 147x. That will tell me definitely where the function's increasing, where it's decreasing, and it will locate any local extreme values. So I set it equal to 0. See, I add 147 to both sides and divide by 3, and I get 49 is equal to x squared. Take the square root of both sides. I get x is plus or minus 7. So I can make my sign diagram, negative 7, 7, f prime, f, and I pick a number in this interval, say negative 8. Out comes a positive number, so it's increasing. And here I pick 0, negative, decreasing. Here I pick 8, and I put 8, I'm putting it back into the derivative. Out comes a positive number. So I can visually see the intervals where it's increasing and decreasing. And I see there's a local max at x equals negative 7, and there's a local min at x equals 7. So to get the y coordinates for the local max and the local min, remember you have to take the values and toss it back into the function because they're actual points on the graph of the function. So when you put negative 7 in there for x, I mean, good grief, what do I get? I get like 972. Wow. When I put 7 in there for x, I get negative 400. Wow. Now I compute the second derivative. So the second derivative is 6x. Second derivative, well, that's equal to 0. It's equal to 0 at x equals 0. So I make a number line, I make a sign diagram. Remember, I put F double prime here, I put F here. Pick a number in this interval, toss it in to see what comes out, positive or negative. Negative, concave down. This would be positive, concave up. So I see intervals of concavity. I see it's concave down. I see where it's concave up. I also see where there's an inflection point. There's an inflection point at the x value of 0. That's where it changes concavity. And the y coordinate is 286. All right, so I think I have enough information to sketch the graph. So let's see. I will, on my y-axis, I'll scale by 300s. On my x-axis, I'll scale by 3s. And let me plot the points. We have a local max at -7, 972. 3, 6, 7, and what was it? 972. So that's, I'm going to say it's about right here. So let me label it. -7, 972. We have a local min at 7, -400. So 3, 6, 7, -400. So I'll say it's about right here. Make it nice and big, make sure I hit it. So 7, -400. And we have an inflection point at 0, 286. So I'll put that about right here. Make sure we hit it. 0, 286. Those 3 points are enough because I know the function's increasing, decreasing, increasing. I know it's concave down on this interval, which means tangent lines would be above the curve. So I'm increasing, decreasing while trying to maintain concave down. Now I switch concavity, still decreasing, and make that a little bigger. And then I start to increase again. That's a nice rough sketch of the graph of the function. And I could always use my graphic calculator to check to make sure. Notice how the calculus would actually help us set our viewing window if we wanted to check with the graphing calculator. All right, part B. Let me bear with me as I erase the board to get part B up here. So part B was to sketch a graph of the function x squared over x squared minus 4. So here's the first thing I would notice before I begin to do anything. This is a rational function. It has vertical asymptotes. This is an old topic we learned, earlier in the course. Vertical asymptotes are the values of x where the denominator is 0, but the numerator is not 0. The denominator here is 0 for x equals -2 and x equals 2. So I would make a note. There are vertical asymptotes at x equals -2 and x equals 2. Similarly, there's a horizontal asymptote. Well, the degree of the numerator is the same as the degree of the denominator. So the horizontal asymptote is the line y equals leading coefficient of the numerator over leading coefficient of the denominator. 1 over 1 is 1. So we have we know there are horizontal asymptotes and vertical asymptotes. So, well, I've gotten you started on this one. So here's what I'd like you to do. Pause the video and you finish it. So finish this example. Use the first derivative to tell you where it's increasing and decreasing and if there are any local maxes or local mins. Use the second derivative to tell you intervals of concavity and if there are any inflection points. And that should be enough information to sketch the graph. So pause the video, finish this example. When you're done, restart the video. I'll be here at the board working through it. Alright folks, I went ahead and wrote down what the derivative is using the quotient rule. The derivative of the numerator times the denominator minus numerator times derivative of the denominator all over denominator squared. And I need to clean this up a little. So if I distribute the 2x, I get a 2x cubed minus 8x. That's a minus 2x cubed all over x squared minus 4 squared. Neat thing happens, the 2x cubes cancel out. So I'm left with negative 8x over x squared minus 4 quantity squared. So that's my derivative. It's a fraction. It looks like a fraction. It's equal to 0 when the numerator's 0. The numerator's 0 at x equals 0. So the derivative equals 0 at x equals 0. Okay, now the derivative is undefined when the denominator is 0, so that's at x equals negative 2 and x equals 2. Now technically speaking, those are not critical numbers for this function because they're not in the domain. You know, you can't be called a critical number unless you're first an element of the domain. You know, but when I make my sign diagram, I do put negative 2 and 2 on the number line, and also 0. But I put negative 2 and 2 on the number line because those are elements not in the domain. It's splitting the graph. It's breaking the graph off. So I need to analyze it separately. So let me put my f prime here and my f here. And if I pick a number in this interval, I say negative 3, and I toss it into the derivative, well, no matter what I put in, the denominator is positive. So a negative comes in here. The numerator, you have a negative times a negative, that's positive. Positive divided by a positive is positive. Function's increasing. Pick a number in here, say negative 1. You get a positive over positive. It's positive. Pick a number in here, say 1. You'd have a negative divided by a positive. That's negative. And out here I'd pick 3. You'd have negative divided by a positive. So I see intervals where the function's increasing and where it's decreasing. I also visually see that we have a local maximum, no local min. And the local max is at 0, 0. So 0, and I put 0 in here, and 0 comes out. Okay, now for concavity, I need to get the second derivative. And already thinking ahead, I'm going to have to do some erasing to finish this problem off. Alright, so here we go with the second derivative. So here's the first derivative. So I get the second derivative. And I have the second derivative, well, we have to use the quotient rule. So it's the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator. And notice when we do the derivative of the denominator, we have to use the chain rule. And then all of that's over the denominator squared. Okay, this needs to be simplified. I'm going to take my time with it. So I have a negative 8 times x squared minus 4 quantity squared. So let's see, a 2x times 2 times negative 8x. See, that's a negative 32x squared. So minus a negative would make plus 32x squared. Okay, that wasn't too bad. In fact, now in the numerator, it looks like I can do some factoring. I could factor out I factor out a negative 8, so I can take a negative 8 out of there. Let's factor out a negative 8 x squared minus 4 to the first power. That's to the first power. So if I factor this out of this term right here, I'm just left with an x squared minus 4 to the first power. Here I would have, a minus 4x squared. Oh, that's it. Well, that's not too bad. Well, you know what? I can continue simplifying. Notice how I could take this x squared minus 4 and cancel it with, you know what? I said it, but I didn't write it down. When I differentiate the first derivative, this should be a fourth power. I'm sorry, I know I said it, but I didn't write it down. I could take this x squared minus 4 and cancel it out with one of the x squareds minus 4 in the denominator. Oh, that will leave me, let me do that. That leaves me with an x squared minus 4 quantity cubed. And then, well, I can combine like terms in here, and I have a negative 3x squared minus 4. You know, I'm gonna do something that's gonna seem a little unorthodox, but I'm gonna distribute this negative 8 back in. Only because I see so many negatives, and I know if I distribute it, I get a 24x squared plus 32. Okay, so now here's why I want to do that. First off, we need to figure out where the second derivative is equal to 0. It's a fraction. The only time it's equal to 0 is when the numerator is equal to 0. That numerator is never equal to 0. No matter what you put in for x, the numerator is going to be at least a 32. Because any negative number gets squared, becomes positive. So in fact, the numerator is always going to be positive. For any value of x, the numerator is positive. I'm going to make that note right now. For any value of x, the numerator is always positive. But I still need to make a sign diagram. And the reason why I still need to make a sign diagram is because these values of x, negative 2 and 2, are where the graph has a vertical asymptote. And I make my sign diagram, you know, I put f double prime here and I put f here. In this interval, I pick any number I want, negative 3, toss it into the second derivative. I know the numerator is positive. Well, when negative 3 comes in here, negative 3 squared is 9, 9 minus 4 is 5, 5 cubed is positive. Positive divided by a positive is positive. Concave up. In this interval, pick any number I want. I pick 0. I know the numerator is positive, but when 0 comes in here for x, I end up with a negative 4 cubed. Negative 4 cubed is negative. Positive divided by a positive is negative. Concave down. And then out here, I'd probably pick 3. So I see my intervals of concavity. I see where the concavity switches, but I do not have any inflection points because the concavity happens to be switching or changing where we have vertical asymptotes. There are no points there. It's a vertical asymptote. Now I think I have enough to sketch the graph, but what I'm going to have to do, I need to keep this up here, and I need to keep this up here. So I need these two bits of information. So here's what I'm going to do. I'm going to bring over here the result of the second derivative. I have the result of the first derivative test there, and I think I have enough to sketch the graph. And you might be thinking, what are you talking about, Bill? You only have 1 point. How can you sketch a graph with only 1 point? Well, it's because of all that wonderful calculus. Okay, first off, we know there are vertical asymptotes at 2 and -2. So let me sketch in the vertical asymptotes. -2 and 2. We know there's a horizontal asymptote at y = 1. So let me sketch that in. We only have 1 point to plot, and that's a local maximum at 0, 0. We can sketch a graph because we know from -infinity to -2 the graph is increasing, and we know it's concave up. I know the graph can't start down here. It can't do that. I know there are no x-intercepts. The graph has to start by hugging the horizontal asymptote. We're increasing, and we're concave up. And that's the meaning of a vertical asymptote. It's going to be shooting off to infinity. Now from -2 to 2, well, I know the function's increasing from -2 to 0. It's a local max. And then it decreases from 0 to 2. I also know on that interval, -2 to 2, it's concave down. Concave down, tangent lines would be above the curve. So I have to start off hugging the vertical asymptote, concave down, I'm increasing, I hit the local max, I start to decrease, but I'm still concave down. I'm adhering to the meaning of what a vertical asymptote is. And then all that's left is the interval from 2 to infinity. Well, from 2 to infinity, the function is decreasing, but it's concave up. So it has to start off hugging the vertical asymptote. That's the meaning of a vertical asymptote. And it's decreasing. Concave up. Tangent lines would be below the curve. And that is my graph. That's a sketch of the graph of this function. And it's probably a pretty accurate sketch. And we did it with only 1 point. So there was one more example. I mean, you know we had to do a trig one. Fun with trig. So let me erase this. Part C. Was the function x plus cosine 2x, only on the interval 0 to pi. So I start off getting the derivative. The derivative is 1. The derivative of cosine is negative sine. And then I have to remember the chain rule. So the derivative is 1 minus 2 sine x. I set the derivative equal to 0. Add this to both sides and then divide both sides by 2. And I have sine 2x equals 1/2. Where does sine equal 1/2? Well, sine equals 1/2 at pi over 6 and 5 pi over 6. So that means 2x must equal pi over 6 and 5 pi over 6. And if we go around the unit circle again, we would get, because the 2 means going around the unit circle again, we get those values, divide each of them by 2, and we get pi over 12 and 5 pi over 12, 13 pi over 12, and 17 pi over 12. And now I realize, you know, these last two we don't care about because it's not in the interval 0 to pi. So I make a sign diagram. On the sign diagram, I I put pi over 12, 5 pi over 12. I also put 0 and pi because we're only on the closed interval 0 to pi. We don't care what's happening to the right of pi. We don't care what's happening to the left of 0. So I put my f prime here and my f here, and I have to think of a number that's between 0 and pi over 12. What do you think? Pi over 24? Put pi over 24 into the derivative, and this is probably where I would quickly use a calculator to evaluate this to see what comes out, positive or negative. And when I do that, a positive comes out, which means the function is increasing. Now in pi over 12 to 5 pi over 12, I could actually pick something that I know is in that interval. I could pick a pi over 6, and I could put pi over 6 in for x. 2 times pi over 6 is pi over 3. The sign of pi over 3 is square root 3 over 2. 2 times square root 3 over 2 is just square root 3. 1 minus square root 3 is negative. And 5 pi over 12 to pi, I have to pick a number that's in that interval. I don't know, what do you think? 11 pi over 24? I mean, you just got to pick something that you know is in that interval, and I would toss it into the calculator. I would toss it in here, use my calculator to see what comes out, and a positive comes out, which means the function is increasing. So now, folks, I see where the function's increasing and where it's decreasing. I see there's a local max at pi over 12. There's a local min at 5 pi over 12. So the local max, I can write that here, is at pi over 12, and then I put pi over 12 back in here to the function to see what comes out. And when I put pi over 12 back in here for x, I get the y coordinate to be pi over 12 plus square root 3 over 2, because 2 times pi over 12 is pi over 6, and cosine of pi over 6 is square root 3 over 2. My local min, well, that occurs at 5 pi over 12, and I put 5 pi over 12 back into the function, and what comes out for y is 5 pi over 12 minus square root 3 over 2. Okay, now, these are points on the curve, and I'm going to have to plot these points when I make the graph. So I would see what the decimal approximation for pi over 12 plus square root 3 over 2 is, and I have that approximation, and I'm just going to write it off to the side here. That's about 1.13, and 5 pi over 12 minus square root 3 over 2, that is close to 0.44. Alright, time for the second derivative. So the second derivative. Okay, the second derivative is, the derivative of sine is cosine, and then I have to remember the chain rule, so I get negative 4 cosine 2x. That's the second derivative. And I'd have to set it equal to 0. I divide both sides by negative 4. So I get, where does cosine equal 0? Well, it's 0 at pi over 2 and 3 pi over 2. I'm not going to make the second trip around the unit circle because of that interval. We get x is pi over 4 and 3 pi over 4. I need to make a number line. Let me block this off so it doesn't get too polluted. On the number line, I need to locate 0. Put pi over 4, 3 pi over 4, and pi. Remember, we don't care what's happening to the right or to the left, to the right of pi or to the left of 0. I put f double prime here and f here. I pick a number in this interval. I don't know. I guess I could pick pi over 6. I put pi over 6 into the second derivative, and out comes a negative, which means concave down. Pi over 4 to 3 pi over 4. I could pick pi over 2. So I put pi over 2 in here, out comes a positive. 3 pi over 4 to pi, 3 pi over pi. I'd pick 5 pi over 6, so I put 5 pi over 6 into the second derivative, out comes a negative. So I see intervals where it's concave up and concave down. I also see inflection points. So we have an inflection point at pi over 4 as 1, and the other one has an x-coordinate of 3 pi over 4. So pi over 4, I've got to put that back into the original function. And we get pi over 4 plus the cosine of pi over 2. Well, cosine of pi over 2 is 0. So the y-coordinate of the inflection point is also pi over 4. Then I put 3 pi over 4 in. I get 3 pi over 4 plus, see, 2 times 3 pi over 4 is 3 pi over 2. The cosine of 3 pi over 2 is 0. So this is kind of freaky. And again, just kind of thinking ahead, I'm going to plot these points. Pi over 4 is about 0.8, and 3 pi over 4 is about 2.4. Alright, so now I think I have enough to graph. I think I have enough to sketch the graph. And this is going to be something else. Alright, so there's x, there's y. Scale the y-axis by 1s. Let's see, the x-axis, I need to go from 0 to pi. Let me split that in half. Pi over 2. Let me split it again. Pi over 4 and 3 pi over 4. Alright, so let's plot the points that we found. Pi over 12, comma, pi over 12 plus square root 3 over 2. So that's pi over 12, and the y-coordinate's about 1.13. So pi over 12. See, this would halfway would be pi over 8, and then halfway again would be pi over 16. So I'm going to say pi over 12 is about right here, and this y-coordinate, so I'm going to plot it right there, and then I'm going to label it as pi over 12, comma, pi over 12 plus square root 3 over 2. And people they're amazed. How do we know where this point is? How do we know that y value? Well, don't tell anyone we used a calculator to get a decimal approximation. So we have that as a local max. Local min, 5 pi over 12, and then this ugly thing, but we know what it's decimally, about equal to. So 5 pi over 12, that's less than pi over 2, and the y is about 0.44, so I'm going to put that about right here, and I'm going to label that as 5 pi over 12, comma, 5 pi over 12 minus square root 3 over 2. So we found our local max, our local min, inflection points are pi over 4, 3 pi over 4, 3 pi over 4. So pi over 4 and about 0.8. So that's about right here. And 3 pi over 4, 3 pi over 4, so that's 2.4, so that's about right here. Alright, so let's try to graph it. We know from 0 to pi over 12 it's increasing, and on that interval it's concave down. So, when x is 0, the y value would be 0 plus cosine of 0. Cosine is 1. 0 plus 1 is 1. So my graph is increasing. Then it starts to decrease, and it's going to hit this inflection point. So it's going to switch concavity now and become concave up. So now it switches to concave up. It has to continue to decrease till we get to the local min, concave up, and then it, let's see, it starts to increase. It starts to increase, and now it becomes concave down again. So it starts to increase, and it's concave, well, it's still concave up. Now I have to finish it off. From 3 pi over 4 to pi, it's concave down. It's still going to be increasing, but it has to switch concavity. So let's see when x is pi. So when pi comes in here for the x's, you'd have pi plus cosine of 2 pi. Cosine of 2 pi is 1. So it's pi plus 1. Pi plus 1, well, that's what, about 4.14? So let me plot that point. That's about right here. So I have to switch concavity and do, well, you know, let me label this. This was an inflection point that was 3 pi over 4, 3 pi over 4. This was an inflection point. Pi over 4, pi over 4. We have the local max labeled, we have the local min labeled, and we say, wow, what an ugly problem. But we did it. The power of calculus. So as I said, there's nothing new in this section. It's just putting everything together. We did 3 examples. You're ready. You can go do the exercises in section 4.4. So at this time, head off and do the exercises in section 4.4. Thanks for watching.